Let me get your attention, please. Go ahead and respond to the poll. And is this? I think this is running. Okay. I hope you guys are okay. I'm doing better, I guess. Not at 100%, but feeling better. Good, well enough to teach. Don't worry, it's not measles. So just a regular old cold. But anyway, I guess I'll start. Well, I don't know. I should ask, how are you guys doing? How's the homework coming along? And I don't know if you have any questions before we get started. Yes?
The derivative of J times B transpose with respect to B, J transpose?
Oh, man. The derivative of J, B transpose with respect to B, I think it's just J. Or no? Okay.
Doesn't work out.
It doesn't work out? I mean, it just ends up being like ones, right? It should be, so. Okay, it's hard to answer off the top of my head. I gotta like write it out. Okay. We can talk through it during office hours and stuff. If you're stuck, don't hesitate to come ask for help. Okay, let's see. Today's lecture. Oh, I didn't put a title, but I think we left off talking about linear regression as a probabilistic model, okay? So at the very beginning of the course, we just said linear regression, you fit this linear model, and we train the model by trying to minimize our errors, okay? And it's a good strategy to minimize errors. It works well. It works for neural networks. It works for linear regression. It works for all sorts of things. If you have a good way to define a loss function or your errors, you can just say, let's make the goal of minimizing our loss. Let's make the goal of minimizing our errors. And of course, we saw the effects of regularization, changing up that loss function. And this week, we said, well, you know what? Let's take a probabilistic approach. Rather than saying our model is just this straight line, we're going to say, yes, our model is this straight line, or whatever it is, linear regression, but the data itself is the result of a random process, okay? That our values are coming from a normal distribution. Just focus on this part here. Our values are coming from a normal distribution where the mean follows that straight line defined by linear regression or multiple linear regression. And but the values themselves are random in that they are randomly distributed with some kind of noise sigma. And I think I had a picture of it back here where it looks like this. This is kind of the true model in blue, and at each location you can imagine just some kind of normal distribution centered at what the model says it is, and then the values are being drawn from there, okay? And if we frame things up that way, then we can say the data that we have has a likelihood function. And so, that, assuming each of our data points are independent, the likelihood function is going to be the product of these independent probabilities. So we have, this product of basically our normal densities. And so if we expand this to our kind of our Gaussian distribution PDF, we're going to get this. And so right now, the likelihood function of our linear regression model, which is formed by w times x, with Gaussian noise is going to look like this, okay? And so the Gaussian noise part looks like this. And we said if we wanted to maximize the likelihood function with respect to w, then our likelihood is this product. Instead of dealing with the likelihood, we'll deal with the log likelihood, so that we don't have to deal with the product, but we get a sum instead. I want to cough into the microphone. We're dealing with a sum rather than a product, and if we take careful look at this log likelihood, we see it's a bunch of constants, and this part looks a lot like the sum of squared errors. And so we left off saying something like trying to maximize the log likelihood is equivalent to minimizing the sum of squared errors, because this part, we're multiplying our sum of squared errors by a negative constant. And so this part's not all that exciting because, well, I don't know if it was ever exciting, but it's not all that exciting because we're arriving at the exact same thing that we found earlier, okay? But it is also kind of exciting in that we took a completely different approach. We just said, our values are coming from some normal distribution centered at this w times x line, and they have Gaussian noise. And because the Gaussian is basically e to a negative quadratic, it ends up, when you try to minimize the log likelihood, you end up minimizing the sum of squares, okay? And so taking kind of a different starting point, we end up at the same solution that we had before. And so we get, I skipped the work here, but I think we've done this work before where we minimize sum of squared errors, and we arrive at this thing where w hat is x transpose x inverse, x transpose t, and minimizing the squared loss, which is what we did in the kind of the first few weeks of class, is equivalent to maximizing the likelihood if the errors are assumed to be Gaussian. Excuse me. I just got to survive to 10:50. All right. And so anyway, this is where it is. We could also take the same approach and say, let's maximize the likelihood function with respect to sigma, okay? Because that's also an unknown parameter. Earlier, we just treated sigma as some fixed value. And it turned out to be okay because it didn't factor into our solution at all. This time, we're going to say, let's maximize the log likelihood with respect to sigma. So I'm just taking this this part right here, I don't know, whatever you call this whole thing, the log likelihood. So that's my starting point, and now I'm going to take the derivative of this with respect to sigma, the partial derivative of this with respect to sigma. And so, this is a constant, so we get 0. N log sigma becomes n over sigma. And then negative 1 over 2 sigma squared becomes positive 1 over sigma cubed, okay? And then this part is just a constant, okay, with respect to sigma, right? And so anyway, this is what we get. You rearrange a few terms, and you get sigma squared is 1 over n times this thing, okay? What is this thing? This over here is the sum of squared errors divided by n, right? So it's the mean squared error, which is pretty much, what's the equation of variance? the variance of something is, so just replace t of n with y and this thing with mu, okay? What is variance? Variance is the exact same thing except it's divided by 1 over n minus 1, right? And why do we even do n minus 1? What's that? To make it unbiased, right? And why does that make it unbiased?
You take the expected value,
So the intuition is that if you know the population mean mu, you could just take your sample observation, subtract it from the population mean mu, and you would take that difference, square them, add them up, and divide by n, and that would be unbiased. Okay. The problem is when you're doing variance yourself, is that you don't know the population mean mu, and so you're estimating the population mean mu based on your sample, right? And so your sample's mean is always going to be closer to the middle of your sample than the true population mean. So you're going to get bias that way, because the true so if you look at your sample and you look at the mean's always going to be in the middle, or it's going to always be the balancing point of the deviations in your sample, right? But if you knew the population mean, it's probably going to be slightly different from your sample mean. And so if you estimate the deviations by taking the difference between your observations and the population mean versus observations in your sample mean, there's going to be a difference which introduces bias. So that's why the n minus 1 comes into correct it. But anyway, this is basically your maximum likelihood estimate of sigma is basically like the variance where you're not doing that n minus 1 bias correction, okay? So it looks a lot like that. And I guess that's all I had to say about that. And then, and this jumps into the topic of Fisher information. I'm just curious, do you guys talk about Fisher information in which class? 100?
B and C.
B and C, okay. Oh, well then maybe this is old hat. Can you guys explain to me what Fisher information is?
The inverse of that is the lower bound.
The inverse of the what? Okay, well, I mean, there's like the Kramer-Rao lower bound, and that comes into play there, right? But I don't know, an intuitive explanation of Fisher information? Maybe? Okay, well, I don't know. Maybe I'm going to try to get at some intuition. Like, you're dealing with like second derivatives and all of that, which, I don't know, maybe there's intuition there. I'm going to do my best, all right? All right, so we're going to just start with talking about derivatives, right? So the derivative tells you like the rate of change of a function, which is like the slope. Okay, that part's okay, right? That's intuitive. All right, and then the second derivative tells you how much that first derivative changes. So it's like how quickly does the slope change, which we can think of as the curvature of a function, right? So if the slope changes rapidly, then that means like it's really curvy. And if the slope changes slowly, then it's smoother. I don't know what to say. And so, you know, large absolute values of the second derivative indicate, you know, sharp bends or very curvy functions and things like that, okay? And then you also learned about like the concavity, where like the second derivative, if it's positive, is going to be concave up, and if it's negative, is concave down, and if it's zero, it's something like, I don't know, saddle points and stuff like that, inflection points, stuff like that, right? So anyway, I think that part's intuitive, right? I think we got some intuition there regarding first and second derivatives. Okay. We're going to generalize this to multivariate functions. I don't know, maybe I should generalize it later, but as far as multivariate functions, you know, the gradient is kind of our equivalent to the first derivative. And and it doesn't point, it's not the slope, the singular slope, because now we're in this higher dimensional thing, but it's a vector that points in the direction of steepest descent, okay? And the negative of that will be the direction of steepest descent. And that's kind of the intuition behind gradient descent, is you calculate the gradient, and if you take it in the opposite direction, you're going downhill, okay? So that's what we get for the gradient. And so if we take the gradient again, or basically the equivalent of a second derivative for a multivariate function, what do we get? Second derivative of a multivariate function is called the, from like, what is it? I don't know, 32A? Huh? The what? The Hessian, right? Do we remember that? Okay. No, but that's what we have, right? So we have, so here's our gradient. It's, you know, the partial derivative, it's the vector of partial derivatives with respect to each component in your vector. And then the Hessian is like the matrix of all the partial partials, right? Like partial with this part and the partial with this part. And it's like, it's all of that. So you get this second derivatives. It's the matrix of all the second derivatives, right? And if you look at this, it's kind of like you take the gradient and you get the partial with respect to the first component and the partial with respect to the second component. And then basically the columns of your Hessian are just, if you treat this and you're going to take the gradient of this and you're going to get, you know, the gradient of this with respect to W1, the gradient of this with respect to W2, the gradient of this with respect to W3, all the way up to Wn, okay? And so that's kind of how the Hessian forms. And yeah, you can go up to n-dimensional things, but you know, we'll just keep it simple and deal with two-dimensional, a 2x2 Hessian, but you get this square matrix, right? Okay, so that's second derivatives, and we'll just pause there and just keep in mind back here when we're talking about second derivatives, it's kind of a measure of how curvy our function is, okay? Okay, so the reason why this Hessian thing is useful is that it informs us about the curvature of the function, okay? And if we apply the Hessian, you know, taking the second derivative of the log likelihood function, or the likelihood function, it gives us an idea of how curvy our likelihood or log likelihood functions are, okay? And that in turn can tell us how confident we can be in our parameter estimates, okay? So I'm going to start off with kind of this univariate example, and I hope this makes sense, and then I don't know, we'll try it for the multivariate thing. And I didn't get to typeset everything at the end, so I'll just talk about it, I guess. All right, so you know, we're going to just start off with this, our silly example, and then so I just, you know, have this pouch. We're going to pretend that there's red marbles and blue marbles in it, okay? And there's some proportion theta that's fixed. We don't know what it is, but we're going to try to guess by taking one marble out at a time and putting it back in, right? It's a stupid thing to do in real life, but it makes for a good example. And so, you know, if I draw 10 marbles with replacement and I say I get 4 red marbles, then our likelihood function is going to look something like this, right? You know, we just multiply the product of each of these probabilities, which is going to be theta raised to the 4th, and then we didn't get red 6 times, so we get 1 minus theta raised to the 6th. Okay, so this is our likelihood function based on our data. And if I plot this, so all I'm doing is just plotting from 0 to 1, you know, theta to the 4th, 1 minus theta to the 6th. This is what our function looks like. And okay, well, the margins are cut off, but it starts off at 0 here, ends up at 1 over here, and this peak happens at 0.4, okay? And basically what I want you guys to see is that, yes, there's a maximum at 0.4, but and it looks nice and pretty, but you know, this also tells us that values like 0.3 and 0.5 and 0.2 and even 0.6, these all have fairly high probabilities, okay, or high likelihoods. And it's only until you get to like 0.9 or 0.01 or something that your likelihood is really low, okay? But you know, with 10 marbles and getting 4 red, there's still quite a high likelihood of, you know, other values other than 0.4, okay? So anyway, this is just in text what I just said there. And on the other hand, we can just keep drawing more marbles with replacement. And so this time I'm going to draw 1,000, okay? And I get 400 red marbles, okay? And so my likelihood function looks like this. We get theta to the 400 and 1 minus theta to the 600, okay? And then when we plot that, our likelihood function looks like this, okay? So still going from 0 to 1, and the spike here is also at 0.4, but it's also, what we see is that it's like way more pointy, okay? In that, you know, the only other values that are kind of likely to produce this data is going to be values like 0.39, 0.41, okay? The value of 0.5 has like almost 0 likelihood of producing our data. Value of 0.3 also has very low likelihood. And so kind of the intuition here is that this thing, having more data, provides us more information about where theta is located, okay? So because I saw 1,000 things, I've got a very good idea of where theta has to be, okay? Theta's got to be close to 0.4. Maybe it's a little higher, maybe it's a little bit lower, but you know, my range of where theta is in this tight band, okay? Where when I only had 10 observations, theta, you know, the most likely value is 0.4, but it could also be like way higher or way lower. We're not like super confident about using 0.4 as our guess. Okay, so to try to relate this back to the second derivative, let's take the log likelihood function, and let's take the second derivative of the log likelihood function. Okay, so here's my log likelihood. So the likelihood is theta to the 4, 1 minus theta to the 6. The log of that's going to be 4 log theta and 6 log 1 minus theta. If I take the derivative of that, I get this. And then if I take the derivative of that, I'm going to get this, okay? The second derivative is going to be this, okay? And then, and basically with 1,000 draws, we just see that this ends up being, you know, 100 times the other thing, okay? So that's the second derivative. And if I punch in, if I evaluate the second derivative at 0.4, I get negative 41.667 versus negative 4,166.7, okay? And basically this just confirms what we saw in the graphs, okay? That, you know, if we think about the second derivative measuring the curvature, how quickly the slope is changing, what it tells us is that the likelihood function of this thing has much greater curvature in that this part, the slope changes much more rapidly than over here, okay? Yes, this is the likelihood and we're looking at the log likelihood, but because the log function is monotonic, it still relates in the same way. In that, you know, the likelihood function or the log likelihood function has much more curvature when we've got a lot more data. Okay, so so this relates it to the Fisher information. Okay, so the Fisher information. Well, okay, sorry. Let's just go back and just talk about kind of this idea of information, which is that the pointy graph has more information than the not pointy one, right? And we have a way to kind of quantify this in a way that kind of makes sense, right? So when we're looking at the second derivative, and we look at how much data we have from 10 observations and how much data we have from 1,000 observations, the 1,000 observations has, if we call this information, this quantity is 100 times bigger than when we had 10 observations, okay? And that kind of makes some kind of intuitive sense. It's a little bit strange because this idea of information, like quantifying your information with a number feels strange, but if there's some kind of measure of like how much knowledge we have and we can put a number on it, to say that you get 100 times more with 1,000 observations than you do with 10 observations, that kind of makes sense, all right? And so this is, this comes together in the Fisher information, and the Fisher information ends up being this equation, right? It's, formally, it's the variance of the score, where the score is the derivative or the gradient of the log likelihood, okay? Here, I guess I'll take the, maybe not the special version, but kind of the version that we're using, is that if the log likelihood is twice differentiable and there's certain conditions are met, then we can say that the Fisher information is also equal to the negative of the expected value of the second derivative of the log likelihood. Okay, so this gets a little bit convoluted, because here we were just talking about the second derivative of the log likelihood, and that kind of made sense. I don't know, maybe it didn't make sense, but I guess my hope is that by talking about the curvature and how pointy the graph is, we get a sense of a way to kind of quantify how confident we are about our parameter estimates here. And so, you know, we're dealing with the second derivative, talking about the curvature of the log likelihood function, and that would be fine and all. But now we're going to talk about, you know, taking the expected value of this thing, and it gets a little bit, I guess, messy. But this is kind of the definition of this. All right. I'm going to bring it back to kind of our Bernoulli experiment. So if we talk about, you know, just again having the pouch. So this time we're going to assume indeed that the pouch is indeed 40% red. Then when we draw a single value, okay, if our random variable x is one draw from the pouch, then the Fisher information will treat as the negative expectation of the second derivative of the log likelihood function. And so the likelihood function for a single Bernoulli draw is this, okay? Theta to the x, 1 minus theta to the 1 minus x. This is the general thing. And then the second derivative, I skipped a couple steps here, but you're going to get this. And the when you take the negative expectation of this, okay, for x, the expected value is going to be theta, okay, for our Bernoulli thing. So we'll just plug in theta here, and so we get theta and 1 minus theta over here, the negative expectation. And if we simplify that, we get 1 over theta times 1 minus theta. And so that's what we have. And then, and because the Fisher information is deals with the log likelihood, more information, basically the log likelihood function of additional observations become just the sum of all of those things. So the Fisher information itself is going to be additive, right? So if you take independent observations, the likelihood function is going to be the product of those independent probabilities, and the log likelihood is going to be the sum of those independent log probabilities. So, so the Fisher information is additive, and so if you have n observations, of a Bernoulli thing, you're going to get n times theta over 1 minus theta, and this is exactly what we had. Or when we had 10 observations, our information is basically going to be the negative of this, and we get 41.667, and then when we had 1,000 observations, it's 100 times that. And so, so here we have Fisher information, okay? I don't know if this is okay. If you can now explain Fisher information slightly. Just think of it as how curvy is your likelihood function, and if it's really curvy, meaning that it's really pointy, you got more information about your parameters, okay? That's kind of the intuition, all right? So the second derivative measures curviness, and that's why the second derivative ends up in our Fisher information thing. And so anyway, that's where we are.
Question.
Yes?
But there's another definition which involves the first derivative. How can you justify the curviness using the first derivative?
How can I justify this with the first derivative? Yeah, it's let's go to Wikipedia. So yes, the original definition is the it's the variance of the score, right? And so the score is the first derivative of the log likelihood, and then the variance of that is this. And let me think. So, well, one attribute is that the score has an expected value of 0. And so if you think of the definition of variance, which has the shortcut definition of the expected value of x squared minus e to the x squared, this part is going to zero out, right? And then so you just now have the expected value of this thing, which is kind of where we get this part.
It explains it right there.
What's that?
It explains it one line below.
Okay. Well, great. Okay, well, thank you, Wikipedia, for saving me the embarrassment of trying to explain myself out of something. Yeah, so this is how it relates the first derivative with this. But again, under certain regularity conditions, yeah, this is the explanation there. Yeah, the formal definition of the Fisher information is the variance of the score. I guess for me, intuitively, I like to think of it as the expected curvature of your log likelihood function, okay? Because for me, that makes a little bit more intuitive sense. Anyway, so we're going to tie this back to our multivariate setting, okay? So what did we say? All right, we said Fisher information is kind of your expected curvature of the log likelihood function, the curvature being the second derivative of the log likelihood function. I guess I should say the negative of that, negative expectation. And so, so for the multivariate thing, the Fisher information for a multivariate function tells us how much information our data has about kind of our multiple parameters. So if you think of linear regression, we've got 2 parameters, W0 and W1. If you've got multivariate, multiple linear regression, you're going to have, you know, more W parameters. And so the Fisher information is going to be your second derivative of that thing, okay, the curvature. And so now you're going to get, for a multivariate function, the second derivative is going to be the Hessian matrix, okay? So rather than getting one value, you're going to get this matrix of values, right? And so your Fisher information matrix is going to basically be all of the partial derivatives of the log likelihood function, the second derivatives of all of these things, second partial derivatives. And so this is as far as I got with typesetting. Okay. All right, so I said, remember this, where we have the log likelihood function. And so now we're going to take the second derivative of this with respect to w, okay? So tying this back to linear regression, this again assumes Gaussian noise, all right? So if we're not assuming Gaussian noise, all of this falls apart, okay? Well, not falls apart, but you've got to do something completely different. So, so here's our likelihood function. It's the product of these Gaussian probabilities. And then so here's our log likelihood function, which is this. And we're going to take the second derivative of this with respect to w. Okay, so we start here. If I take the first derivative, or the gradient, with respect to w, I'm going to get this. Okay, and I skipped a few steps. But we end up here, okay, where the gradient of this is going to be 1 over sigma squared x transpose t minus x transpose xw. This part shouldn't look all that unfamiliar, because when we set this equal to 0 and we solve for w, this is where we get the x transpose x inverse x transpose t business. And then if I take the derivative of this with respect to w once more, I get negative 1 over sigma squared x transpose x w. Okay, and this is as far as I got as far as typing up my notes. So I'm going to have to switch over to pen mode. But I don't know, maybe I can just plot this out as well. So this is did I? Oh yeah, this w needs to go away. That's a typo. Okay. Yes. Okay. Here we go. Much better. Yes, so the w goes away, and we get negative 1 over sigma squared x transpose x. Okay, and so let me just talk about this briefly. How do I move this? Okay. Oh. There we go. Okay. All right, so we have the second derivative of the log likelihood function. Okay, and so so there's a few things to note here, right? One is, and if the Fisher information is basically the negative expectation of this, of basically the second derivative, okay, which we plug in there. This ends up, you know, this is a constant with respect to w, okay? So so our negative expectation just ends up being 1 over sigma squared x transpose x. Okay, and so so there's a few things to take note here. One is that if the random noise has a large sigma, we have less information. And that makes sense, right? Let me see. So the idea being, let's say you have one thing where you got so here we've got very little noise, okay, and then over here we've got something like this, okay? So if the blue line represents the true model, true relationship, and over here we've got, here's our true relationship. Okay. Depending on our random sample, our fitted values, okay, might look something, right? So okay. So depending on our random samples, our fitted values could look something like this, where how do I draw a straight line? Okay. So for something like this, depending on your random noise, maybe you'll get a line that looks like that, or a line, depending on your random values, maybe it looks like that. Maybe it ends up over there, okay? Because you get different random noise, right? Whereas over on this plot, depending on your random noise, maybe you get something that looks like that, or something that ends up there, or down like this, okay? Depending on the random observations that show up in our data, okay? And so basically, and I think this makes intuitive sense, is that when we have less noise, we can be more confident about our estimated slope and intercept than when there's a lot more noise in our observations, right? So when there's less noise in the observations, we can be more confident in our estimates of W0 and W1 versus when there's lots of noise. Okay, and so this so this is just kind of a way to quantify it when we throw it into the Fisher information matrix. Okay. Okay. The other part is that we've got this X transpose X. Okay, and it's hard to. I think I'll just throw in a couple extra slides in the notes to kind of talk about that. But basically, there's a few things that go in there. If your X is bigger, meaning you have more observations, this number is going to be bigger. You're going to have more information, okay? And so that's going to play a role in there as well. Okay, we'll end there for today. Have a good weekend, you guys. We'll see you next week.